Hello everyone, welcome to this tutorial. My name is Emerson Ahrori. I'm a Google Earth Engine specialist. In this tutorial, I'm gonna show you how to calculate the association between dust storms and wind speed. As you can see in this plot, there is a linear relationship between the dust activities and also the wind speed. And here I will show you how to make such kind of plots and how to calculate its associations using a scatter plot, correlation analysis, and regression analysis. This tutorial is helpful for those of you who are interested to study on air quality and Earth observation satellite data analysis. If you want to learn how to these steps, please follow this tutorial and share it with other users. So, let's make a new notebook in the Colab environment. In the first step, we need to call essential libraries with necessary to work with the Earth engine from Colab environment. Import EE and GEE map. Another one is the XEE. These are essential libraries currently you need to use in the Python if you want to use Google Earth Engine capabilities in this environment. So, and another library, Xarray, imported as XR. Only XEE is not available, so we need to install it first. So, and another one is matplotlib.pyplot as PLT. This library uses for visualization purpose. That's why we need to import it for the visualization and also plot steps. So let's run the cell in the first step. These libraries are essential when you want to start programming in Google Earth Engine from Python environment. However, maybe we need more libraries in the next steps. I will show you how to call them again and how to use them for each step. For example, in the first step, we need to use the EE library to establish a connection or establish a link connection between Earth Engine and Colab environment. We need to connect to the Earth Engine account through the authentication process and initial your account information. So please enter your cloud project name associated with your Google Earth Engine account. If you want to find it, it is easy. Just go to the code editor environment, upper right, click on account information, and then project info. You can find your cloud project name. Just copy and paste, just like that. And another one is OPTURL. The OPTURL is the address we need to use when you are coding with the XEE library. The XEE is a revolutionary library developed by Google community, allowing us to bring Earth observation images from Earth Engine into Python environment with X-ray format. Then we can apply a wide range of machine learning tools on a satellite data. So as you can see here, the XEE is available here. And if you search on the net about the XEE, you will find a GitHub page, a detailed instructions about how to use and what's the benefit and what is, and also a full explanation about each part of XEE structure. So as you can see, just I'm copy and paste like this, and that's enough. Just copy the URL and run your code. So there is a pop-up here asking you to have access to your Earth Engine account. Click on OK and select the associated account. Then click on continue and continue. After a few moments, you can see we established a connection, meaning that from now on you can use Earth Engine capabilities and functions in the Colab environment. The next step is about the region of interest. I need to identify the region of interest before further analysis with Earth observation data. Create a variable from GEE map called the map function with the base map. For example, a satellite view preferred. So let's run the map. You will have a user interface allowing you to select the region of interest. For example, my own country, Iran, always suffering from dust storms, specifically in the western areas. For example, this part of Iran, southwest in the north of Persian Gulf, always suffering from the dust storms coming from the Saudi Arabia, Iraq, and other Middle Eastern countries. So these areas highly affected by the dust storm each year. So in this tutorial, I'm gonna select this area. However, you can use this tutorial for your own region of interest, not only the region I'm working, because in this tutorial you will learn how to calculate the associations between the dust situation and the wind speed. So now select the region of interest using the drawing tools. I'm selecting southwest of Iran, just like that. In the next step, I need to have the rectangle as a variable. I need to bound the satellite data based on this area. So make a new variable and then select the last feature drawn by the drawing tools, convert it into a geometry, then let's print. You will have a polygon with 5 coordinates showing the actually the process of creating ROI was fine and there is no problem there. So the next step is about to call the satellite data. I need two kind of data. The first, a proxy shows the dust events. If you search on the net, or if you are working about the dust situation, definitely you know about PM 2.5. So thanks to awesome GEE community catalog, this dataset, the monthly version with 1 kilometer spatial resolution, is available for the years between 2000 to from 2000 to 2019. So, and also in the global scale. I'm gonna use the monthly version for 5 years in this tutorial. So let's copy the monthly data here, and then as you can see in the new cell, a new variable created. So here we have an image collection. You can skip the rest of the code because that format is usable in the JavaScript environment, but we are coding based on a Python. That's why for the variable we need to skip the var or var at the first. So there is only a single band here. I'm gonna select it and rename to, for example, PM. So, and then we want to filter our data based on a period of time. For example, from 2000 to 2015, just like this. And let's run the PM. As you can see, 60 elements, the monthly PM 2.5 is available, and each one of them including one single band as PM. In the next step, we need to call the wind speed data. There are various datasets on the net, but I prefer to use the TerraClimate in this tutorial because it is also monthly and wind speed already calculated in this product. So wind speed at 10 meter from surface. So win the speed sets to, so make a tuple like this and enter the image collection snippet. So then select the target band. There are several bands already here, but the VS is the target band or the band we're looking for. So then we need to filter to make a same filter date for the VS, just like this. Again, starting from 2010 to 2015, just like that. So but there is a scale factor for the VS dataset, meaning that we need to multiply this dataset to this value. So, through a map, we are making a loop structure. Lambda, this is an unknown function. Consider each image in the loop structure that is divided or that is multiplied to 0.01. So that's the result. Each VS image multiplied to the scale factor to get the data in a valid range. Then we need the properties of input images for the output. Among the properties, the system time start is the parameter explaining the date acquisition that is necessary for the further analysis. Because everything we are doing here is based on a time and acquisition date, and it is a kind of time series application. So the system time start is necessary. Without that, we cannot go any further. But there is a problem here about the dot copy properties. The IMG doesn't have properties. There is a typo here. I hope it's actually okay now. As you can see, we have 60 elements, same as the PM, this time for the VS, wind speed. There is a one band including the wind speed. So in the next step, we need to combine these two collections in a one single collection. So we have 1 PM and associated VS for the same time. So in the next step, I'm going to use the join structure from using Google Earth Engine to actually bring these two separated data set into a single one. We want to have a same collection with two image, one of them PM and wind speed for each month. So to do this, we need to write a bit, we need a bit more scripting process in the Earth Engine side. Everything I'm doing here is using Earth Engine capabilities. After a few steps, we should move to the Python capabilities. But currently, we are actually using Earth Engine capabilities. So Earth engine.join.inner. I'm gonna use the inner join process here. So we need an equal filter because we want to say that okay, we have two collections and please find the same system time start between these two. Earth engine dot filter dot equal. Actually, the equal filter is actually that tool allowing us to find the same system time start. We have two collection here, so there is two fields. One of them left field and another one is right field, and both of them equals system time start. In the input collections, please find those collections or those images in which their system time start is same. So now we want to combine the equal filter and the join tool or command together with the existing collection. So now another variable join collection created. put all of the process into image collection format, just like this, and then get the join, inner join that is applying on. So three arguments necessary here: two satellite data. The first two arguments belongs to the satellite data. We have two collections, PM 2.5 and wind speed. And the third one is about our condition, about the system time start, that is the filter. So now let's run and see what join collection including. So as you can see here, we have 60 elements again, but this time there are two properties named as primary and secondary. But these are the properties, and we need to bring them back into bands for each date separately. So that's why, so another variable created, collection sets to get the join collection and make a loop structure. So make a function inside a loop. Each input element consider it as EL. You can set any other name. So, and then we want to make a stack image for each date. From element get the primary first. As you can see, we have one property as primary and another one as secondary. So primary, then el dot get, this time secondary, just like that. So, and collection dot cat means they are stacking instead of the simple properties. So let's print, and now we have an same collection with 60 elements, but this time you can see for each time or for each date, two data set is available, or two bands are available, the PM and the wind speed. Okay, now the data set is ready and we can go for the further analysis. So now here we have an image collection structure that is actually a unique structure for the time series satellite data in the Google Earth Engine platform. But thanks to the XEE, we can convert this structure into X-array structure. And then in the X-array, we can apply a wide range of machine learning tools and functions that are available in the Python environment. So that's why XEE is a revolutionary library for the Google Earth Engine users. So now make a new variable as a data set. From XR library, we want to import a new data set. So the collection is a collection. The image collection name is collection, and the engine should be based on EE, CRS, or coordinate system EPSG 4326. This is unique ID for WGS84 and same for all around the world. So the pixel size, as we are using EPSG, the 4326 or WGS84, the scale value is based on a degree. For example, 1 degree sets equals 100 kilometer, but 0.1 10 kilometer. So before set a spatial resolution, you can check the existing data resolution, and then before setting the pixel size, you can consider the amount of the amount of the spatial resolution in such kind of data. As you can see, the MODIS is 1 kilometer and the Terra climate is 5 kilometer. You can consider something between 1 and 5, for example 2 or 3 kilometer as a mid value, because we are dealing with the same data set but with different spatial resolution. You can choose something between. But in this tutorial, I don't want to use spatial information. I'm gonna get the average in the over the region of interest, and that's why not necessarily high resolution is applicable for my study. So I prefer to reduce the spatial resolution to 10 kilometer because I need only a one single value or one average from the region of interest to find the associations. But if I wanted to visualize the spatial pattern, in that case, yes, the scale value should be higher, set to the reality, and because I needed to see the spatial pattern. So that's why spatial resolution considered 10 kilometer for this area. And the next parameter is the geometry or region of the interest. Let's run. After a few moments, you will have the image collection into a new in a new format or the new structure. So as you can see here, we have a multi-dimensional structure, three dimension, one of them time, another one longitude, and another one latitude. You can have a preview by clicking on this icon, and two variables are available, PM 2.5 and wind speed. So, but we need to get the average wind speed and PM 2.5 for the whole selecting area because I don't want to actually use the spatial pattern, just I'm gonna use their temporal pattern through the time and compare them and explain their associations because in each study the target of processing is different, and that's why sometimes spatial information used or sometimes we are using only the temporal information or spatial information or sometimes both of them together. So now let's calculate the average, sets to get the ds and calculate the average. As I said, we have different dimensions, but I need to get the spatial average over the time. That's why latitude and longitude considered as the main dimensions. ds average, let's run. You can see we have different values for PM and wind speed through the time for the selected period. So in the next step, I'm gonna convert it into a data frame structure because in the data frame structure it is easier to do the analysis, and most of the algorithm in the machine learning to completely fit with the data frame structure, and we will have no problem in this regard. So the data frame sets to get the ds average converted to a data frame just like that. Let's print, and here you can see what we have here: a table with three columns, time, PM, and VS. For each time, its associated values are available. Okay, in the next step, as you can see in the initial example, I'm gonna make a plot to show how they are, how actually they are varying from one time to from one month to another month. So I'm gonna show their temporal behavior or their temporal dynamics. So from make a plot like this. First define a figure and axis. From PLT called the subplots. We want to have a fixed size with these dimensions, 10 and 3 for example. So or 10 is a little bit high, for example 8 and 3 a little bit smaller and better for this tutorial. So now I'm gonna add the, for example, PM 2.5 data in the first step. So for the x, call the x and dot plot. Make a plot for the axis. From a data frames, select the index to explain the temporal information, and the next column is, for example, the PM. So let's run, and here you can see the variations or temporal variations of PM 2.5 in a plot simply and without any challenge. So in the same time, I'm gonna show the associated wind speed for each month, but the problem is the range of the values in the wind speed and PM 2.5 is not same. So we need to solve this problem. We need to make another axis and to show the wind speed variations without any change in the visual perspective uh, PM 2.5 value. So I need to define another axis. So x dot twin x do this process easily. So in the new axis, I'm gonna make a bar plot. So the horizontal axis will show the index and vertical one show the wind speed values. So I need to actually set a different color, for example, the red, and the width of each column should be, for example, 50, and let's run. So, but it's a little bit hard to figure it out what is their difference because the previous plot completely covered by the new plot. So we can reduce the width, for example, to 30, and also we can add another parameter like alpha to actually increase the transparency here, and then you can easily understand about the, yes, there is, about the temporal dynamics between these two parameters. So you can see, uh, you can easily understand that there is a almost linear relationship between wind speed and dust events. So the PM 2.5 is a proxy of the dust. When we have a dust event, the amount of the particle matter increases over the region. At least in the region I'm working is like that. So as you can see, when we have the higher wind speed, the PM 2.5, because the wind carrying the particles and aerosols, and when the wind speed increases, meaning that we will have more aerosols and more actually dust in the air. And as you can see here, there is a linear relationship between these two parameters, at least in this region. So, and you can see the linearity between these two parameters. So, but in the next step, I'm gonna understand how much statistically they are associated and how much they are correlated to each other. So we can use some sort of simple statistical analysis, such as the correlation. For example, in this area, I found for this period of time 76% correlation between wind speed and PM. So in the next step, I need to understand if this correlation is significant or not. That in this step, to do this, the regression analysis is very helpful. So, and then you can also make a scatter plot to make sure about their behavior to see that if they are fitted linearly or not. So, from the PLT, make a scatter plot, but this time between PM and wind speed. So now you can see most of the values scattered around this line, and also showing and following the correlation analysis, we can make sure there is a linear relationship. So if there is a linear relationship, then we can use the linear regression to make sure to understand about the significance of this relationship. So, or the linear regression will also help us to understand how much they are dependent and how the another variable changes if one of them change. So now we need to define two variables, x and y. For example, the x here will be the wind speed. We need to understand how much wind speed impact on the dust event in these areas. So we want to have it only values without the time information, and then y sets to the PM values without x information. But remember that we need to import stats models dot I think it is API, or we can do it like this, import statsModels.api as SM, for example. Yes, the stats models is one of the typical statistical libraries mostly used by the users for some sort of a statistical analysis. So here you can see we have X and we have Y. So a series of values for two variables. But we need to add a constant in the OLS regression analysis before calculating the regression. So from SM library, we want to add a constant value. We should do it for the linear regression analysis. But here you can see after the constants added, we will have a constant value next to the wind speed values that should be available for the linear regression analysis. So the next step is about making the linear model. So the model from SM, ordinary least square regression, called, and then we want to fit this model to understand how much they are correlated, or if the relationship or association is significant or not. So the model is run, and now we want to see the results, the model.summary, just like this. Let's run, and you will have a very interesting report here that explaining each factor separately. And the first thing is about the p-value. If the p-value is less than 0.05, meaning that the correlation or the association between these two factors is significant. So the x1, or the wind speed, the x1 means the wind speed here, and as you can see, the x1 association with the PM 2.5, the p-value is 0, meaning that we can say this correlation is actually completely significant with a 95% accuracy, so, or precision. And you can see the R square is about 58%, meaning that 58% of the PM 2.5 dynamic or temporal variation depends on wind speed, and that's how or the way we are explaining these relationship. And also another thing is about the coefficient. For example, coefficient is 14, meaning that if we keep everything constant and only focus on the wind speed and dust, or PM 2.5, based on this relationship, we can understand that if 1% or 1 unit one unit increases in the wind speed equals to 14 units increase in the particle matter. So, or the density of the particle matter, or the average of particle matter. And that shows how actually that shows the uh, behavior or the contribution between wind speed and PM 2.5. You can get a lot of information from this summary, but here I'm only explaining some statistical approaches that you can find to analysis and get understanding about the significance between these two kind of parameters. So finally, as a conclusion, we can see a linear relationship between wind speed and PM 2.5, and correlation is 76%, and regression analysis prove that this relationship is completely significant with 95%, and also we realize that if one unit increases in the wind speed causes 14 unit increases in the other parameter, that here is PM 2.5. I hope you liked this tutorial as much as I did. If you have any question or any problem, feel free to share your questions on my YouTube channel. I will look into it and try to answer you as soon as possible. Thank you for your attention.